Alright, thanks for watching, and today I want to show you a super important fact. Namely, if f is a real function that is continuous and one-to-one, then its inverse function is also continuous. In other words, this explains why functions like arctangent or square root of x or even ln of x are continuous. So, let me first of all remind you of what an inverse function is. So suppose you have a function f from, let's say, an interval I to its range f of I. And f of I is just a set of all the outputs. F of x, where x is in I. Then, if f takes you from x to, let's say, y equals f of x, then it turns out under certain circumstances there is an inverse function which you can just think of it as a return flight. Namely, if f goes from x to y, then f inverse just goes from y to x. And what I basically want to show you is that if f inverse exists, then it is continuous. So fact, if, again, I is an interval and f goes from I to f of I is a continuous and one-to-one. Okay. So in particular, it is onto its image, and therefore there's an inverse function f inverse, then f inverse, which goes from the opposite, from f of I to I, is also continuous. And I like to remind you how is f inverse defined. So simply, if f of x equals y, so if f goes from x to y, then f inverse goes back from y to x. So f inverse of y equals x. Alright, and now let's show this. It is quite a delicate argument, but quite beautiful in my opinion. So first of all, notice the following. So proof. So step one. Now, since f is continuous and one-to-one, if you remember the previous video I did, I showed something beautiful, namely f has to be either strictly increasing or strictly decreasing. So first of all, again, since f is continuous and one-to-one, then f is either strictly increasing or f is strictly decreasing. So without loss of generality, assume just the first case. So assume f is increasing. And first of all, I'm claiming that if f is increasing, then f inverse is also increasing. And let's prove that. Claim. And we'll need this somewhere at the end actually. F inverse is also increasing, and for this, suppose y1 and y2 are in f of I, so are in the domain of f inverse, and y1 is less than y2, and what we want to show is that f inverse of y1 is less than f inverse of y2, but then, by definition of f of I, what we know is that y1 is of the form f of x1, so it is of the form f of something, and y2 is of the form f of something else for some x1 and x2 in the interval. Alright, however, what do we know if for some reason x1, again just by contradiction, if x1 is greater than or equal to x2, then since f is increasing, we would get f of x1 is greater or equal to f of x2. But then by definition, this means that y1 would be greater or equal to y2. But this contradicts the fact that y1 is less than y2. Therefore, it is not the case that x1 is greater or equal to x2. Therefore, what we have is that x1 is less than x2. But what is x1? Well, since f of x1 is y1, x1 is just f inverse of y1. And similarly, x2 is f inverse of y2. Okay, it's kind of the return flight, and therefore what have we shown? We assumed y1 was less than y2, and we've shown that f of y1 is strictly less than f. So f inverse of y1 is strictly less than f inverse of y2. Now that we've proven the little fact, let's now go back to our essential and show that our function is continuous. So step 2. So just a little bit of notation to make things easier. Let j be f of I. Okay? And in particular, notice since I is an interval and f is continuous, I have shown that f of I is an interval as well. So j is an interval, and also g, let's just call that f inverse. So f inverse is just g. Okay, and what we have to show, in particular, one thing though, g is then from f of I to I, so from j to I, and what we have to show is that g is continuous. So show g is continuous at x naught, and that's for all x naught in j. Alright, now, x naught is a point in that interval j. Okay, so this is j, this is x naught, and well, without loss of generality, we can just assume that x naught is not one of the endpoints. Because otherwise you just repeat the proof, and then it was very similar if it's an endpoint. So assume x naught is not an endpoint of j. And what do I mean by that? I mean, let's say for instance j is the interval 3, 5, assume x naught is neither 3 nor 5. And here's what I'm claiming, because look, you have x naught, well, you can apply g to it to get g of x naught, to get some point in I, and I'm claiming that g of x naught is also not an endpoint of I. So claim g of x naught is not an endpoint either. It's not an endpoint of I. And why is that? So suppose not. In particular, suppose for instance that g of x naught is the left endpoint. And again, super similar for the right endpoint. So suppose g of x naught is the left endpoint. And in particular, you'll see why this is useful. Well, let x be any element in j. Okay? So let x in j be arbitrary. All right, but then in particular, if you apply g to x, you get here a g of x. Okay? But then g of x is in the interval I. Is in I, but here's the thing, g of x naught is the left endpoint. So in particular, by definition, g of x naught has to be smaller than g of x. So by definition, g of x naught has to be less or equal to g of x. But then I'll just apply f to this, because remember f is increasing. Therefore f of g of x naught is less or equal to f of g of x. So again, f is increasing, but now remember, g is just f inverse. So f undoes whatever g does, so you get x naught is less or equal to x. But then what does that mean? I'm telling you, for any arbitrary point here, x naught is smaller than that arbitrary point. But this could only happen if x naught is the left endpoint of the interval j. X naught is the left endpoint of j, which contradicts the fact that x naught is an endpoint of j. But x naught is not an endpoint. Of j. That's a contradiction, and therefore we actually get that, well, x naught is not an endpoint of j, and in particular it must be inside of j. So hence we get that g of x naught is inside the interval I. Or if you know some metric spaces, it's in the interior of I. I know, that word you really like. But then since it's inside, so in the interior of I, it means if you move around a little bit, you're still in I. So in particular, for R small enough, we can guarantee that g of x naught plus r and g of x naught minus r are still in that interval. So there is some r small. Hence there is r small with g of x naught minus r, comma, g of x naught plus r is inside your interval. And notice, I still haven't defined epsilon, like 10, 15 minutes away in, and still haven't done epsilon yet. But now we'll do it. So step 3. So let epsilon be given. Alright, and the point is, epsilon is very small. So it's okay to assume that epsilon is less than r. So assume epsilon is less than r. But then here's the point. Since the ball of radius r is inside your interval I, in particular, the ball of radius epsilon is also inside your interval I. So in particular, we have that if you take the closed interval, g of x naught minus epsilon, g of x naught plus epsilon. So kind of this red ball, it's inside the blue ball. G of x naught minus r, g of x naught plus r, and that's inside of the interval. In particular, the two endpoints here, this and this, are in I. So definitely those 2 points here are in your interval. Hence, we know that g of x naught minus epsilon and g of x naught plus epsilon are in I. Okay, and you'll see that the rest of the proof is super interesting. Not that it was boring so far, but now it's like it gets very exciting. Because again, this is g of x naught. This is g of x naught plus epsilon. This is g of x naught minus epsilon. And again, this is in I, and then this is maybe in j. And in particular, notice g goes from x naught to g of x naught. However, moreover, notice that, well, g itself is onto, because it's invertible. So since g, again, g goes this way, g from j to I is onto, again, because it's invertible, we actually get that those 2 points are of the form g of something. So, and g of x naught minus epsilon and g of x naught plus epsilon are in I, we actually get that g of x naught minus epsilon is of the form g of something, so g of x1, let's say, and g of x naught plus epsilon is of the form g of something, where that something is also in j. So for some x1 and x2 in j. In other words, there are some x1 and x2 here, such that g of x naught minus epsilon is g of something. So such that x1 maps to this specific point, and then this is of the form g of x2. Okay. So remember this, that's very important, and remember in particular, what do we want to show? We want to show that if we're close enough here, then g of x is in that good region. And remember the good region is this one, because this has size epsilon. Alright, however, we do need to show that this picture is correct. So let's show that x1 is less than x0 is less than x2. Now, okay, on the one hand, what do we have? So if we claim x1 is less than x0 is less than x2. Alright, we do know that g of x0 minus epsilon is less than g of x0 is less than g of x0 plus epsilon. But then this thing here, that's of the form g of something. So g of x1 is less than g of x0 is less than g of x2. And now just apply f to this, because remember f is increasing. F of g of x0 is less than f of g of x2. And now remember that g is just f inverse. So all this is just the identity, and therefore f of g of x1 is just x1, f of g of x0 is just x0, etc., etc. So in the end, you're left with x1 is less than x0 is less than x2. And there you go. Alright, and now we're finally ready to define our delta. So notice between x1 and x0, there's this distance here, and also this distance here. So just let delta be the smaller one of the two distances. So step 4, let delta be the smaller one of x1 minus x0 and x2 minus x0. And why do we do this? Because then, if x is in the ball centered at x0 in radius delta, then for sure, x must be between x1 and x2. But then the point is, we'll show that g of x is between g of x0 minus epsilon and g of x0 plus epsilon, which is really the good region, which is the stuff we want stuff to be in, and then we would be done. So then, if x minus x0 is less than delta, then we get that x is between x1 and x2. And now finally, we can use the fact that g is increasing. So we haven't used that until now. So now g of x1 is less than g of x is less than g of x2. Again, because g is increasing. But now remember, g of x1 is just g of x0 minus epsilon. And that's less than g of x. and that's less than g of x naught plus epsilon. And therefore we're basically done. Subtract g of x naught from this g minus Giovanni. We get that it's between minus epsilon and epsilon. And in particular, this is true for absolute values. So then absolute value of g of x minus g of x naught is less than epsilon. And we are finally done with this proof. All right, congratulations. So from now on, you can assume that inverse functions are continuous. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.